How the redshift of gravitons explains dark matter and dark energy. Firmin J. Oliveira. Affiliation: East Asian Observatory / James Clerk Maxwell Submillimeter Telescope. March 3, 2023. Abstract. The theory that gravitons lose energy by way of gravitational redshift while traveling in a gravitational field is applied to the expansion of the universe and to spiral and dwarf galaxy rotation curves using Newtonian physics and general relativity. This is a graviton self-interaction model which derives an expansion equation which is identical in form to the standard lambda cold dark matter model. In the domain of galaxies, spiral and dwarf galaxy rotation curves are matched using only baryonic mass. Thus, the requirement for dark matter and dark energy in the universe is replaced by this paradigm. Keywords: gravitons, gravitational redshift, baryon mass density, supernovae, spiral galaxies. Prelude. This is an audio-oriented version of the paper How the Redshift of Gravitons Explains Dark Matter and Dark Energy by Firmin J. Oliveira, Journal of Modern Physics, 13-11, November 2022. DOI 10.4236/JMP.2022.13111084, which is open access. No major changes were made, except to improve the audio rendering by placements of spaces in equations and plus signs to some exponentials, etc. Caveat: the document reader performs well with text but has difficulty with mathematics. Thus, text have been included after each numbered equation and after a few inline mathematics for better articulation. We apologize for any inconvenience this may cause. Introduction. This paper describes a theory of gravitons acting in the universe, and it supersedes the theory expressed in reference 1 in regards to the expansion of the universe. We will also describe the action of gravitons in galaxies, reference 2. Assuming that gravitons are the agents of interaction in a gravitational field, then our goal is to describe how the gravitational redshift of gravitons shows up as what has traditionally been labeled as dark matter and dark energy. We will show how the redshift of gravitons can explain both of these phenomena using high-precision data. Throughout this paper, all reference to sources of mass and test particles are assumed to be of baryonic nature, unless otherwise specified. When we speak of the graviton mass mg, it is a relativistic mass. We assume gravitons are bosonic particles which travel at constant speed c in vacuum, where c equals the speed of light. Gravitons traveling in a gravitational field between a source mass m and a test mass m, modeled by the equivalence principle as an accelerating system, should experience an average energy loss of delta xi. Introduction. Due to motion in that field, over a short time period delta t equals delta r/c, where the acceleration at a point r in the field is given by a equals minus gm/r2, that is, a equals minus gm over r squared. The energy loss is expressed differentially as delta xi equals minus mgc2, delta v c equals minus mgc, at delta t equals minus gmmg r2 delta r1. That is, delta psi equals minus the quantity mg c squared and quantity times delta v over c, which equals minus mg times c a delta t, which equals minus the quantity g mmg over r squared and quantity times delta r, equation 1, where mg equals m/n is the average relativistic graviton mass, n is the number of gravitons, m is the test mass, delta v is the change in the free fall velocity of the system observed from an inertial reference frame, g is Newton's gravitational constant, m is the baryonic mass of the field source. R is the distance between the center of the source and the location of the moving gravitons, delta t is the short travel time of the gravitons. Introduction. At speed c over distance delta r, the energy change is a loss, negative, because the velocity change delta v is in the same direction as the motion of the gravitons, so that for an inertial observer moving in the same direction as the graviton, the energy of the graviton is redshifted. We call this effect of energy loss a gravitational redshift, which, as we have described it, resembles a Doppler effect. Since gravitons are agents of the gravitational field, our model is essentially an attempt to describe the graviton-graviton interaction as in the self-interaction of a quantum gravity theory. Reference 3. Gravitons exist and travel in a gravitational field, which in principle is equivalent to an accelerating system. Assume that the total graviton energy for a system of two masses is expressed by psi equals gmm. R. 2. Introduction 4. That is, psi equals gmm over r, equation 2, where m equals nmg is the total graviton mass associated with the test mass m, where mg is the average graviton mass and n is the number of gravitons. The total graviton energy decrease delta xi due to its freefall in the gravitational field of mass m, when viewed from an inertial system, is expressed by delta xi equals minus psi delta v c equals minus gmm. R delta v c equals minus gmm. RGM. C2R2 delta R, 3. That is, delta psi equals minus psi times delta v over c, which equals minus the quantity gmm over r and quantity times delta v over c, which equals minus the quantity gmm over r and quantity times the quantity gm over c squared r squared and quantity times delta r, equation 3, where, as in equation 1, delta v equals gm slash c r2, delta r, that is, delta v equals the quantity gm over c r squared and quantity delta r, is the velocity increase in the accelerated. Introduction v. Reference frame equivalent according to the principle of equivalence to the gravitational field of mass m at the position r. Gravitons in an expanding universe. Consider the universe as a sphere of interior baryonic mass m with a thin spherical shell of mass m. The masses m and m are constants. The thin shell has a radius r, t, at time t. Only the mass interior to the shell has an effect on the shell. The total graviton energy psi, t, within the shell at time t is given by equation 2, where r equals r, t. Assuming isotropic uniformity, the mass density ρ, t, within the shell at time t is ρ, r, t, equals 3m 4 pi r 3, t. 4. That is, ρ of r of t equals 3m over the quantity 4 pi r cubed of t and quantity, equation 4. At the present epoch of time t0, the baryon mass density is ρb, which is given by ρb equals 3m 4 pi a 3, 5. That is, ρb equals 3m over the quantity 4 pi a bar cubed and quantity, equation 5, where a equals r, t0, is the radius of the universe at the present epoch. Energy loss due to gravitational redshift. Since the potential function phi, r, equals gmm slash r is defined as having zero energy at infinity and having a negative energy at position r, likewise we define the graviton energy loss to be zero at infinity and negative at position r, applying equation 1 to the n gravitons in free fall in the expanding universe. We have the energy loss. Increments idm equals kdmz increments I. 0 n delta xi equals minus kdmz r. Infinity minus gmm. R2 dr equals minus kdm gmm. R, 6, that is, delta psi dm equals k dm times the integral from 0 to delta psi of the quantity and delta psi and quantity, which equals minus k dm times the integral from infinity to r of the quantity minus gmm over r squared and quantity delta r, which equals minus k dm times the quantity gmm over r and quantity, equation 6. where kdm is a coupling constant to be determined by observation and the extra minus sign accounts for an energy loss because the gravitons travel in the same direction as the free fall velocity change and appear redshifted to an inertial observer also moving in the same direction. Energy loss due to expansion I. Substituting for m from equation 5 and simplifying yields. Increments idm equals minus kdm 4 ga 3 m rho b r 7. That is, delta psi dm equals minus k dm times the quantity 4 pi g a bar cubed over 3 end quantity times the quantity m rho b over r end quantity, equation 7. This component is the energy loss of the so-called dark matter. Gravitons traveling at speed c in the vacuum of the expanding universe undergo cosmological redshift in 3 dimensions on the way to interaction with the masses. We express this redshift by applying the 3D velocity differential, delta Vx delta Vy delta Vz slash c3, that is, delta Vx delta Vy delta Vz over c cubed, to the total graviton energy psi from equation 2, and applying equation 3, in the 3 spatial dimensions, given in the form delta xi equals minus gmm r. Delta Vx, delta Vy, delta Vz, C3, 8. Energy loss due to expansion 2. That is, delta psi equals minus the quantity gmm over r end. Quantity times the quantity delta Vx, delta Vy, delta Vz over c cubed. End quantity, equation 8, where the negative sign is applied. Because the motion of the gravitons is in the same direction as the freefall in the field, we can convert the 3D velocity differential to a ratio of 3D volume differential by the construction delta Vx, delta Vy, delta Vz. C3 equals delta x c delta tx, delta y c delta ty, delta z c delta tz equals delta x, delta y, delta z. C 3 delta tx, delta ty, delta tz, 9. That is, the delta Vx, delta Vy, delta Vz over c cubed equals the quantity delta x over c delta tx times delta y over c delta ty times delta z over c delta tz and quantity, which equals delta x delta y. Delta z over the quantity c cubed delta tx delta ty delta tz end. Quantity, equation 9, where x, y and z are Cartesian coordinates. Tx, ty and tz are independent times and where delta Vx equals delta x slash delta tx, delta Vy equals delta y slash delta ty and delta Vz equals delta z slash delta tz. Furthermore, we convert the energy loss due to expansion 3 volume differential in Cartesian coordinates to radial coordinates, in the form delta x, delta y, delta z equals 4 pi r to delta r. 10. That is, delta x delta y delta z equals 4 pi r squared delta r, equation 10. Now, applying the transformations equation 9 and equation 10 to equation 8, while also moving the volume differential C3 delta Tx delta Ty delta Tz, that is, C cubed times delta dx delta Ty delta Tz, to the left-hand side of the equation we get delta xi, C3 delta Tx delta Ty delta Tz, equals minus gmm r, 4 pi r, 2 delta r. 11. That is, delta psi times the quantity c cubed delta tx delta ty delta tz end quantity equals minus the quantity gmm over r end quantity times 4 pi r squared delta r, equation 11. The left-hand side of equation 11 is a quadruple differential, whilst the right energy loss due to expansion 4 hand side is a single differential. Integrating both sides of equation 11 yields A 3D increment d equals z t0 z t0 z t0 z increments I0 delta xi, c3 delta tx delta ty delta tz equals z r0 minus mgm s 4 pi s 2 delta s equals z r0 minus 4 pi m gm s delta s equals minus 8 pi 2 g 3 a 3 m rho br 2. 12. That is, the quantity a bar cubed over sigma dE end quantity times delta psi dE equals the integral from 0 to t, the integral from 0 to t, the integral from 0 to t, the integral from 0 to delta psi of the quantity delta psi times c cubed delta tx delta t y delta tz end. Energy loss due to expansion V. Quantity, which equals the integral from 0 to r of the quantity minus m g m over s and quantity times 4 pi s squared delta s, which equals the integral from 0 to r of the quantity minus 4 pi m g m s delta s and quantity, which equals minus the quantity 8 pi squared g over 3 and quantity times a bar cubed m rho br squared, equation 12. Where the expansion time is taken to be t equals a/c, 13. That is, t equals a bar over c, equation 13, where a is the present radius of the universe and d is a dimensionless coupling constant and where, in the final line we substituted for m from equation 5. Rearranging equation 12, we get the graviton energy loss due to the expansion of the universe, the so-called dark energy component. Increment d equals minus d 8 pi 2 g 3 m rho br 2. 14. Energy loss due to expansion 6. That is, delta psi dE equals minus sigma dE times the quantity 8 pi squared g over 3 and quantity times m rho b r squared, equation 14. We will subsequently show that the graviton energy losses increments IDM and increment d can account for the expansion rate of the universe without dark matter or dark energy, which are required by the lambda-cold dark matter cosmological model, reference 4. Equation of the expanding universe I. The total energy of the shell of mass m, where mm, that is, m much less than m, having kinetic energy, gravitational potential energy, and energy loss due to the cosmological redshift of gravitons equation, 14, is expressed by 1 2 mv2 minus gmm r plus increments idm plus increment d equals 1 2 mv2 minus 4 ga 3 m rho b r minus kdm 4 ga 3 m rho b r minus d 8 pi 2 g 3 m rho b r 2 equals minus 1 2 mc2 ca 2, 15. That is, 1/2 mv squared minus the quantity g m m over r end quantity plus delta psi dm plus delta psi de equals 1/2 mv. Equation of the expanding universe 2. Squared minus the quantity 4 pi g a bar cubed over 3 end quantity times the quantity m rho b over r end quantity minus k dm times the quantity 4 pi g a bar cubed over 3 end quantity times the quantity m rho b over r end quantity minus sigma d e times the quantity 8 pi squared g over 3 end quantity times m rho br squared, which equals minus 1/2 m c squared k a bar squared, equation 15, where the term on the far right is the total energy, where k is a constant, curvature, with dimensionality, length, minus 2, that is, length to the minus 2, a is the present radius of the universe and m is the mass of the universe. Multiplying equation 15 by 2/Mr 2, that is, 2 over m r squared, and simplifying, we get the expression for the expansion of the shell. V2 R2 equals 8 ga 3 rho b 3 1. R3 plus kdm 8 ga 3 rho b 3 1. R3 plus d 1 6 pi 2 g rho b 3a3 minus kc 2a2. R2 16. Equation of the expanding universe 3. that is, v squared over r squared equals the quantity 8 pi g a bar cubed rho b over 3 and quantity times the quantity 1 over r cubed and quantity plus k dm times the quantity 8 pi g a bar cubed rho b over 3 and quantity times the quantity 1 over r cubed and quantity plus sigma d e times the quantity 16 pi squared g rho b over 3 a bar cubed and quantity minus k c squared a bar squared over r squared, equation 16. Note that the shell mass m can be made arbitrarily small compared to the universe mass m. Define the distance r by r equals a 17. That is, r equals a bar times a, equation 17, where the time-varying scale factor a is dimensionless with 0 a less than or equal to 1. Using equation 17, the velocity v takes the form d equals dr dt equals a to dt. 18. Equation of the expanding universe for. That is, v equals dr by dt which equals a bar times dA by dt, equation 18. Substituting equation 18 into equation 16 gives us 1 a to dt 2 equals 8 pi g 1 plus kdm, rho b 3 a 3 plus 1 6 pi 2 deb 3 minus kc2 a 2. 19. That is, the square of the quantity 1 over a times dA dt and quantity equals 8 pi g times the quantity 1 plus k dm and quantity times rho b over the quantity 3 a cubed and quantity plus the quantity 16 pi squared g sigma dE rho b over 3 and quantity minus k c squared over a squared, equation 19. Puting equation 19, in terms of the mass densities we have 1 a to dt 2 equals 8 pi g 3 rho m a plus rho dm a plus d a plus rho k a 20. That is, the square of the quantity 1 over a times dA dt and quantity equals the quantity 8 pi g over 3 and quantity times the equation of the expanding universe v quantity rho m of a plus rho dm of a plus rho dE of a plus rho k of a and quantity, equation 20, where rho m a equals 1 plus kdm rho b a 3, 21. That is, rho m of a equals the quantity 1 plus k dm and quantity times rho b over a cubed, equation 21, is the mass density composed of baryons and graviton energy loss mass due to gravitational redshift, and apparent dark matter mass density. d a equals 2 deb, 22. That is, rho dE of a equals 2 pi sigma dE times rho b, equation 22, is the graviton energy loss due to the expanding universe, and apparent dark energy mass density, and rho k a equals minus 3 kc 2 8 got 2, 23. Equation of the expanding universe 6. That is, rho k of a equals minus 3 kc squared over 8 pi g a squared, equation 23, is the curvature mass density. Define the Hubble parameter h, t, by h, t, equals 1 r dr dt, 24. That is, h of t equals 1 over r times dr by dt, equation 24. Where, by equation 17, r equals a, that is, r equals a bar times a. Equation 24 can also be written as d equals dr dt equals h, t, r, t, 25. That is, v equals dr by dt which equals h of t times r of t, equation 25, which is the Hubble law for h0 equals h, t0, where t0 is the present epoch of cosmic time. Thus, h, t, defined by equation 24, is the general form of Hubble's law, reference 5. Equation of the expanding universe 7. Substituting h, t, for dt in equation 20, with some manipulation, we get rho c, t, equals 3h2, t, 8. Pi g equals rho m, t, plus d, t, plus rho k, T 26. That is, rho C of T equals 3h squared of T over 8 pi g, which equals rho M of T plus rho dE of T plus rho K of T, equation 26, where rho C, T, is called the critical mass density at time t, dividing equation 26 by rho C, T, yields the parametric equation. Rho C, T. Rho C, T equals C equals 1 equals M, T, plus D, T, plus K, T, 27. That is, rho C of T divided by rho C of T equals omega C, which equals 1, which equals omega M of T plus omega dE of T plus omega K of T, equation 27, where M, T, equals rho M, T, slash rho C, T, D, T, equals D, T, slash rho C, T, and K, T, equals rho K, T, slash rho C, T. That is, omega. Equation of the expanding universe 8. M of T equals rho M of T over rho C of T, omega dE of T equals rho dE of T over rho C of T, and omega K of T equals rho K of T over rho C of T. At the present epoch T0, the mass density parameter is M, T0, equals 1 plus kdm, B, 28. That is, omega M of T0 equals the quantity 1 plus kdm and quantity times omega B, equation 28, where B is the baryon mass density parameter. The graviton expansion energy loss mass density parameter is D, T0, equals 2 deb, 29. That is, omega dE of T0 equals 2 pi sigma dE times omega B, equation 29, and the curvature density parameter is K, T0, equals minus K, C2H20. 30. Equation of the expanding universe 9. That is, omega K of T0 equals minus K, C squared over H0. Squared, equation 30. General relativity for an expanding universe with graviton. Interaction I. The Friedmann-Lemaitre-Robertson-Walker, FLRW, metric line element, references, 6, 7, 8, 9, in terms of the scale factor A, T, is ds2 equals minus c2 dt2 plus a 2, t, dr2. 1 minus 2 krona plus r2 d theta 2 plus r2 sin 2, theta, d phi 2, 31. That is, ds squared equals minus c squared dt squared plus a squared of t times the outer quantity d r squared over the quantity 1 minus k r squared end quantity plus r squared d theta squared plus r squared sin squared theta d phi squared end outer quantity, equation 31, where the scale factor 0, a, t, less than or equal to 1, that is, a of t greater than 0 and less than or equal to 1, and the curvature k has units of length, minus 2 where k0 or k equals 0, that is, k less. General relativity for an expanding universe with graviton. Interaction 2. Then 0, k equals 0 or k greater than 0. The Einstein equations, reference, 10, 11, in trace reverse form is R nu equals kappa T nu minus 1 2 Tg nu, 32. That is, R mu nu equals kappa times the quantity T mu nu minus 1 half T times G mu nu end quantity, equation 32, where R nu, that is, R mu nu, is the Ricci tensor, T nu, that is T mu nu, is the energy momentum tensor, T is the contracted energy momentum tensor, G nu, that is G mu nu, is the metric tensor defined by equation 31, and kappa equals 8 pi g slash c4, that is, kappa equals 8 pi g over c to the fourth. General relativity for an expanding universe with graviton interaction 3, define the energy momentum tensor T nu of a perfect fluid. T nu equals Rho C 20000 P 000 P 0000 P 33. That is, T mu nu equals the tensor with rho C squared, P along the diagonal with zeros everywhere else, equation 33. Where, referring to equation 21, to equation 23, for the mass densities, the total mass density rho is given by rho equals rho m plus d plus rho k, 34. That is, rho equals rho m plus rho de plus rho k, equation 34, where rho m equals 1 plus kdm, Ba 3 R3, 35. General relativity for an expanding universe with graviton interaction 4. That is, rho m equals the quantity 1 plus k dm and quantity times rho b times a bar cubed over r cubed, equation 35. D equals 2 deb, 36. That is, rho de equals 2 pi sigma de times rho b, equation 36. Rho k equals minus 3k a2c2 8 pi gr2, 37. That is, rho k equals minus 3k a bar squared times c squared over 8 pi g r squared, equation 37, and where the current baryon mass density is rho b equals rho cb, 38, that is, rho b equals rho c times omega b, equation 38, where b is the baryon mass density parameter. We have assumed the general relativity for an expanding universe with graviton. Interaction V. Equation of state for the relativistic particles PD equals dc2, that is, PDE equals omega dE rho c squared, with d equals minus 1. We are neglecting the radiation density, photon and neutrinos, and we will justify this when we fit the model to ESNA IA data. Solving the Einstein equations, 32, given the mass-energy tensor equation, 33, and simplifying the results, yields the equation for the rate of change of the scale factor. A 2 equals 8 pi g3 rho minus k a2. 39. That is, the square of the quantity a d over end quantity equals the quantity 8 pi g over 3 end quantity times rho minus the quantity k over a squared end quantity, equation 39. Assuming general relativity for an expanding universe with graviton. Interaction 6. K equals 0 for no curvature, and the total mass density given by equation 34 to equation 38, the Hubble parameter h, a, is h, a, equals h0 r, 1 plus kdm, b a 3 plus 2 deb, 40. That is, h of a equals h0 times the square root of the outer quantity of the quantity 1 plus k dm end quantity times omega b over a cubed end outer quantity plus 2 pi sigma de omega b end square root, equation 40, where b equals 8 pi g rho b slash 3h20, that is, omega b equals 8 pi g rho b over 3h0 squared. Fits to type Ia supernova data and comparison with the standard model I. The scale factor has the relation to the cosmological redshift c expressed by A equals 1 plus c. 41. That is, A equals 1 over 1 plus c, equation 41. An increment of comoving distance, delta dc, defined in terms of the scale factor is delta dc equals c dt a equals c de a 2h, a, 42. That is, delta dc equals c times dt over a, which equals c times dA over a squared h of a, equation 42, where we used the definition equation 24 of the Hubble parameter. In terms of the cosmological redshift c, the comoving distance is delta dc equals c dzh, z, 43. Fits to type Ia supernova data and comparison with the standard model 2. That is, delta d c equals c times dz over h of z, equation 43. where we used the fact that d equals minus dz slash 1 plus c, 2 equals minus a 2 dz, that is, d equals dz over the square of the quantity 1 plus c and quantity which equals minus a squared dz, to transform equation 42, dropping the minus sign. The flux phi0 from a distant light source at redshift z is defined in terms of the observed luminosity LO equals L slash 1 plus c, 2, that is, LO equals L over the square of the quantity 1 plus c and quantity, where L is the luminosity of the emitting source. Phi0 equals L 4 pi, 1 plus c, 2 d2p, 44. That is, phi0 equals L over the outer quantity 4 pi times the quantity 1 plus c squared and quantity times dp squared and outer. Fits to type Ia supernova data and comparison with the standard model 3. Quantity, equation 44, where dp is the proper distance. The luminosity distance, from equation 44, is 1 plus c, dp equals r L 4 pi phi 0. 45. That is, the quantity 1 plus c and quantity times dp equals the square root of L over 4 pi phi 0 and square root, equation 45. The luminosity distance, from equation 43, is dl, z, equals 1 plus c, dc equals 1 plus c, zz. 0. C do H, U, 46. That is, dl of z equals the quantity 1 plus c and quantity times dc which equals the quantity 1 plus c and quantity times the integral. Fits to type Ia supernova data and comparison with the standard model 4. From 0 to z of c du over h of u, equation 46, where dc is the comoving distance and where h, z, equals h0q, 1 plus kdm, b, 1 plus c, 3 plus 2 deb, 47. That is, h of z equals h0 times the square root of the quantity 1 plus k dm and quantity times omega b times the cube of the quantity 1 plus c and quantity plus 2 pi sigma de times omega b and square root, equation 47, and we change the negative sign to positive by inverting the limits of integration. The form equation 47 of the Hubble parameter h, z, is identical to that of the standard model. Therefore, fitting to the ESNA Ia data will be identical. The magnitude is defined in the standard way. Mu, z, equals 5 log, dl, z, minus b plus AF, 48. Fits to type Ia supernova data and comparison with the standard model V. That is, mu of z equals 5 times the log of the quantity dl of z and quantity minus mu b plus a off, equation 48, where b is the source magnitude and AF is an offset. Generally, the source magnitude is combined into AF. We applied equation 48 in a fit to 580 type Ia supernovae, ESNA Ia, magnitude data from the Supernova Cosmology Project Union 2.1 data set. Reference, 12. With Hubble constant h0 equals 70 km s-1 mpc-1, densities m equals 0.271, d equals 0.729, reference, 12, and offset AF equals minus 87.441, the fit to the ESNA Ia data set obtained a 2-parameter chi2 is equal to 0.9769. That is, chi squared equals 0.9769. Figure 1 shows the fit to the data. Regarding neglecting the radiation density in our model, the radiation density parameter of photons, with h equals 0.7 is given by, reference, 13, r equals 2.47 times 10⁻⁵, slash h2 is equal to 5.04 times 10⁻⁵. That is, omega r equals 2.47 times 10 to the minus 5 over h squared, which fits to type Ia supernova data and comparison with the standard model 6 equals 5.04 times 10 to the minus 5. at the maximum redshift of max equals 1.5 for the SNIA data, the relative magnitude of the error. Rad in comparing the radiation and matter densities is rad equals R, 1 plus max, 4. M, 1 plus max, 3 equals 4.6 times 10 minus 4, 49. That is, rad equals omega r times the fourth power of the quantity 1 plus c max end quantity over omega m times the cube of the quantity 1 plus c max end quantity, which equals 4.6 times 10 to the minus fourth power, equation 49, which justifies ignoring the radiation density in the fitting. Assuming that the curvature k equals 0, so that k equals 0, then from equation 27, we have for the present epoch 1 equals 1 plus kdm, b plus 2 deb, 50. Fits to type Ia supernova data and comparison with the standard model 7. That is, 1 equals the quantity 1 plus k dm end quantity over omega b plus 2 pi sigma d e times omega b, equation 50, and from equation 29, d equals d2 pi b. 51. That is, sigma dE equals omega dE over 2 pi omega b, equation 51. For example, for d equals 0.721 and b equals 0.049, which is in the Big Bang nucleosynthesis, BBN, allowable range, reference, 14, we get a value of the coupling constant d equals 2.342. Also, from equation 28, we get kdm equals m slash b minus 1 is equal to 4.694. The expansion time, from equation 13, has the value t equals 1 slash h0 is equal to 13.97 by 109 years, that is, t equals 1 over h0, which equals 13.97 times 10 to the 9 years. Fits to type Ia supernova data and comparison with the standard model 8. Figure 1. Supernova Cosmology Project Union 2.1 ESNA Ia magnitude versus redshift data points with error bars. The solid line is the fit for the graviton model with m equals 0.271 and d equals 0.729 with a 2-parameter. Fits to type Ia supernova data and comparison with the standard model 9. Chi2 is equal to 0.9769. The dotted line is the fit for the LCDM model with the same parameters and the same Chi2, the graviton model and the LCDM model fits are, obviously, identical. Gravitons and galaxies I. Integrating equation 1 up to radial distance r, we obtain the average energy change per graviton increments Ig expressed by increments Ig equals minus CV 0, mg C2, do C equals minus Cr 0 milligrams GMB S2 ds. 52. That is, delta psi g equals minus the integral from 0 to v of the quantity mgc squared end quantity times do over c, which equals minus the integral from 0 to r of mg times the quantity g m b over s squared end quantity ds, equation 52. Equation 52 describes the gravitational redshift of the energy of the average graviton as it travels from a lower, more negative potential to a position r of higher, less negative potential and is consistent with energy conservation. Now, consider the energy for a galaxy of mass m interior of a small mass m in a circular orbit of radius r. The gravitons traversing the distance at light speed from the interior mass to the orbiting mass. Gravitons and galaxies too will experience a decrease in energy as described by equation 52, increments I equals n increments Ig, where n is the number of gravitons. Taking the energy loss of the gravitons into account, the total orbital energy of the orbiting mass m is 12 mv2 minus gmm r plus kg n increments Ig equals E, 53. That is, 1/2 mv squared minus the quantity g m over r end quantity plus k g times n delta psi g equals E, equation 53. Where v is the rotational velocity of the orbiting mass, kg is a coupling coefficient, a constant for each galaxy, and the total energy equals minus gm/2r. Using equation 53, by expanding increments ig using equation 52, with m equals nmg, multiplying by 2/m and moving all terms except v2, that is, v squared, to the right-hand side, we obtain the expression for the orbital velocity. v2 equals gm r. r plus 2 kg zr. 0. gms. S2ds. 54. Gravitons in galaxies 3. That is, v squared equals the quantity gm of r over r end quantity plus 2k g times the integral from 0 to r of the quantity gm of s over s squared end quantity ds, equation 54. As an approximation, we model the mass distribution of a spiral galaxy by a spherically symmetric distribution ρ, r, even though a mass density distribution consisting of a spherically symmetric central bulge surrounded by an axially symmetric thin disk would be more realistic. Then the mass m, r, of the galaxy within the radial distance r from the galaxy center is given by m r equals z r. 0 4 pi rho s 2 ds. 55. That is, m of r equals the integral from 0 to r of the quantity 4 pi rho of s times s squared ds end quantity, equation 55. Coupling coefficient kg I. Under our assumption that the coupling coefficient is constant for each galaxy, equation 54 can be solved for kg at the galaxy edge, where r equals rf and v equals vf, giving kg equals v2f minus gm rf rf 2r rf0 gm r r2 dr 56. That is, kg equals the outer quantity vf squared minus the quantity gm of rf over rf end quantity end outer quantity over the outer quantity 2 times the integral from 0 to rf of the quantity gm of r over r squared end quantity dr end outer quantity, equation 56, where m rf equals mb is the total baryonic mass in the galaxy. By Newton's gravitational law, at the galaxy edge, the final velocity vf is related to the total mass mg, contained within the radial distance rf by v2f equals gmg rf equals g, mb plus md. rf, 57. Coupling coefficient kg2. That is, vf squared equals gmg over rf, which equals g times the quantity m b plus m d end quantity over rf, equation 57. Where mg equals mb plus md, where md is the total apparent mass due to the graviton energy loss, the mass of the so-called dark matter. The total apparent dark matter in a galaxy is given at the galaxy edge by md obs equals v2 f rf g minus mb, 58. That is, md obs equals the quantity vf squared times rf over g and quantity minus mb, equation 58. Using the results from analyzing galaxy rotational data, we can estimate the dark matter by equation 58 as md, and substituting that and equation 57 into equation 56, we arrive at a formula for estimating kg as kg equals md obs 2 rf r rf 0 m r r2 dr. 59. Coupling coefficient kg3. That is, kg equals md obs over the outer quantity 2 rf times the integral from 0 to rf of the quantity m of r over r squared end quantity dr and outer quantity, equation 59. The Einstein equations for galaxies with gravitons I. Assuming a spherically symmetric mass distribution for a galaxy, we will use the Schwarzschild metric to describe the motions within the galaxy. The Einstein equations for the region outside of a spherical mass distribution is R nu equals 0, 60. That is, R mu nu equals 0, equation 60, where R nu, that is, R mu nu, is the Ricci tensor. The metric element we use is defined in spherical coordinates. ds2 equals minus e nu c2 dt2 plus e lambda dr2 plus r2 d theta 2 plus sin 2 theta d phi 2 61. That is, ds squared equals minus e to the nu times c squared dt squared plus e to the lambda times dr squared plus r squared times. The Einstein equations for galaxies with gravitons 2. The quantity d theta squared plus sine squared theta d phi squared and quantity, equation 61, where E nu equals 1 minus 2 gm, r. C2r, 62. That is, e to the nu equals 1 minus 2 gm of r over c squared r, equation 62. E lambda equals 1 minus 2 gm, r. C2r minus 1, 63. That is, e to the lambda equals the outer quantity 1 minus the quantity 2 gm of r over c squared r and quantity and outer quantity to the minus 1, equation 63, and where m, r, is the mass within radius r. From the metric element equation 61, the metric tensor is G nu equals minus e nu 0000 e lambda 0000 r 20000 r 2 sin 2 theta 64. The Einstein equations for galaxies with gravitons 3. That is, g mu nu equals the tensor with minus e to the nu, e to the lambda, r squared and r squared sine squared theta along the diagonal, with zeros everywhere else, equation 64. Since the metric equation 64 does not depend on time t and angles theta and phi, it follows from Hamilton's principle and the Lagrange equations 1 that d tau e nu dt d tau equals 0, 65. That is, d tau of the quantity e to the nu times dt by d tau and quantity equals 0, equation 65, implying that the total energy E is E nu dt d tau equals E mc2, 66. The Einstein equations for galaxies with gravitons 4, that is, e to the nu times dt by d tau equals E over mc squared, equation 66, from which we get E nu c2 dt 2 d tau 2 equals E minus nu e2 m2c2. 67. E to the nu times the quantity c squared dt squared over d tau squared and quantity equals E to the minus nu times the quantity E squared over m squared c squared and quantity, equation 67. And similarly, for the phi component, we have that d tau r 2 sin 2 theta d phi d tau equals 0, 68. That is, d by d tau of the quantity r squared sine squared theta d phi by d tau and quantity equals 0, equation 68, implying that the specific angular momentum is r2 sin 2 theta d phi d tau equals h, 69. The Einstein equations for galaxies with gravitons v. That is, r squared sine squared theta times d phi by d tau equals h, equation 69, from which we get r2 sin 2 theta d phi 2 d tau 2 equals h2 r2. 70. That is, r squared sine squared theta times d phi squared over d tau squared equals h squared over r squared, equation 70. For motion in the plane defined by r and phi, d theta slash d tau equals 0, where theta is defined as theta equals pi 2. 71. That is, theta equals pi over 2, equation 71. 1 Wikipedia, Schwarzschild geodesics, https://en.wikipedia.org/Schwarzschild geodesics. Equation of motion I. We derive the equation of motion using the metric element equation, 61, where ds2 equals minus c 2 d tau 2, that is, ds squared equals minus c squared d tau squared, where d tau is the differential of proper time tau. Dividing the metric element by d tau 2, that is, d tau squared, and substituting from equation 66 to equation 71, with the metric element we get, dropping the theta term since d theta equals 0. ds2 d tau 2 equals minus c 2 equals minus e minus nu e2 m2c2 plus e lambda dr2 d tau 2 plus h2 r2 72. That is, ds squared over d tau squared equals minus c squared, which equals minus e to the minus nu times the quantity e squared over m squared c squared and quantity plus e to the lambda times the quantity dr squared over d tau squared and quantity plus h squared over r squared, equation 72. Multiplying equation 72 by e minus lambda and simplifying yields. dr2 d tau 2 equals e minus nu plus lambda e2 m2c 2 minus e minus lambda c2 plus h2 r2 73. Equation of motion 2. That is, dr squared over d tau squared equals e to minus the quantity nu plus lambda and quantity times the quantity e squared over m squared c squared and quantity minus e to the minus lambda times the quantity c squared plus h squared over r squared and quantity, equation 73. Substituting for e minus lambda, that is, e to the minus lambda, from equation 63 into equation 73, and since e lambda equals e minus nu, that is, e to the lambda equals e to the minus nu, from equation 62 and equation 63, so that e minus nu plus lambda equals e0 is equal to 1, that is, e to minus the quantity nu plus lambda and quantity, which equals e to 0, which equals 1, we get after simplification. dr2 d tau 2 equals e2 m2c 2 minus c2 plus 2 gm r minus h2 r2 plus 2 gm r h2 c2 r3 74. That is, dr squared over d tau squared equals the quantity e squared over m squared c squared and quantity minus c squared plus the quantity 2 gm of r over r and quantity minus the quantity h. Equation of motion 3. Squared over r squared and quantity plus 2 gm of r times h squared over the quantity c squared r cubed and quantity, equation 74. We assume that the mass m, r, within distance r from the galaxy center is given by the sum of the baryonic mass mb, r, within r and the mass mg, r, equivalent to the graviton gravitational redshift energy loss mass within r. The mass density of the baryons is given ρb, r. The total mass within r, which is the sum of baryonic mass and gravitonic energy loss mass, is expressed by m r equals mb, r, plus mg, r, 75. That is, m of r equals mb of r plus mg of r, equation 75, where the baryonic mass is mb, r equals z r 0 4 pi s 2 rho b s ds 76. Equation of motion 4. That is, mb of r equals the integral from 0 to r of the quantity 4 pi s squared rho b of s ds and quantity, equation 76, where rho b is the baryonic mass density, and from equation 54, we express the gravitonic energy loss mass in terms of the baryonic mass density by mg, r equals 2 kg r z r. 0 mbs S2ds 77. That is mg of r equals 2 kg r times the integral from 0 to r of the quantity mb of s over s squared ds and quantity, equation 77. Where kg is a constant coupling coefficient which is peculiar to each galaxy. For circular motion, the specific angular momentum term in equation 74 is h2 r2 equals gm r 78. Equation of motion v. That is h squared over r squared equals gm of r over r, equation 78. Dropping the constant terms in equation 74 and substituting with equation 78, the velocity of a particle in orbit in the galaxy is expressed by d2 equals dr2. d tau 2 equals gm r plus 2c 2 gm r c2r2 79. That is v squared equals dr squared over d tau squared, which equals the quantity gm of r over r end quantity plus 2c squared times the square of the quantity gm of r over c squared r end quantity, equation 79. Results for spark galaxies I. We use the velocities from the Spitzer photometry and accurate rotation curves, SPARC, database, reference, 1516, derived from near-infrared, NIR, surface photometry at 3.6 m. We select the spiral galaxies NGC 2403, NGC 2841 and dwarf galaxies DDO 154 and NGC 2915. From the photometric data which has been reduced to the equivalent velocities for the galaxy bulge, disk and gas mass content, we approximate the baryonic mass as due to a spherically symmetric distribution, which is given by the Newtonian relation for the velocity to mass contained within the radius r from the galaxy center, expressed by mb r equals rg gas r plus upsilon dsk r ddsk r ddsk r plus bull r 80. Results for spark galaxies 2. That is, mb of r equals the quantity r over g end quantity times the quantity absolute v gas of r times v gas of r plus upsilon disk of r times absolute v disk of r plus upsilon bulge of r times absolute v bulge of r times v bulge of r end quantity, equation 80. Where r equals re, I equals 1, 2, n greater than 1, n the number of radial distances observed, and the absolute values of the velocities are needed because they can sometimes be negative, reference, 16, page 5. The velocities for the disk and gas from the table 2 of, reference, 15, are taken with upsilon asterisk operator equals 1, that is, upsilon star equals 1. In our table 2, upsilon dsk and bull, that is, upsilon disk and upsilon bulge, are the m/l, that is, solar mass to solar luminosity ratio, used in equation 80 to make the fits. Using the spark results for the mass at r in terms of the gas, disk and bulge velocities, where the mass internal to r is given by mb r of equation 80, the equivalent graviton energy loss mass is mg r equals 2 kg r sigma n j equals 1 z rj plus j less than 2. rj minus j greater than 1. mbs S2ds 81. Results for spark galaxies 3. That is, mg of r equals the quantity 2 kg r end quantity times the sum from j equals 1 to n of the integral from r of j minus the logical quantity j greater than 1 end quantity to r of j plus the logical quantity j less than 2 end quantity, the integrand being the quantity mb of s over s squared end quantity ds n sum, equation 81. The predicted velocity equation, 79, is expressed in the form d2 rn equals g mb Rn plus mg, Rn. Rn plus 2c, 2g, mb, Rn plus mg, Rn. C2Rn. 282, that is, b squared of Rn equals g times the quantity mb of Rn plus mg of Rn and quantity over Rn plus 2c squared times the square of the outer quantity g times the quantity mb of Rn plus mg of Rn and quantity over c squared times Rn and outer quantity, equation 82, where n equals 1, 2, n greater than 1. We strive to obtain good fits to the velocity VOBs, Rk, at each radial distance Rk by minimizing the mean absolute error MAE. Results for spark galaxies for between V, Rk, and VOBs, Rk, while iterating upsilon dsk, Rk, that is, upsilon disk of Rk, for the disk and, when available, bowl, Rk, that is, upsilon bulge of Rk, for the bulge. We constrained the mass to agree with the baryonic Tully-Fisher relation, BTFR, reference, 1718, mass for each galaxy. Table 1 lists, for each galaxy, the baryonic mass MB determined by the velocity profiles used in equation 80, the BTFR estimated galaxy mass, the mean data rotation velocity error var, the mean absolute fitted error MAE, and the coefficient kg. Table 2 lists the average values for disk upsilon dsk and bulge bull, that, disk upsilon and bulge upsilon, mass to light ratios which were used in making each galaxy fit. Also listed in the table are minimum and maximum upsilon dsk taken from Table 4 and Table 5 of, reference, 19, for comparison. The fitted spiral galaxy disk mass to light ratios are upsilon dsk less than 1.0, that is, upsilon disk less than 1.0. Except for NGC 2841, which fitted with upsilon dsk less than 2.0, that is, upsilon disk less than 2.0. A good reference for fits to spark data can. Results for spark galaxies V also be found in, reference, 20, especially for spiral galaxy NGC 2841, where from our table 2 we have an average of upsilon dsk equals 0.856 m/L and bull equals 1.254 m/L, each of which is of the same order of magnitude as the fitted values. Disk equals 0.81 plus or minus 0.05 m/L and bull equals 0.93 plus or minus 0.05 m/L, respectively, from Figure 1 of, reference, 20. That is, where from our table 2 we have an average of upsilon disk equal 0.856 m solar to L solar, and upsilon bulge equals 1.254 m solar to L solar, each of which is of the same order of magnitude as the fitted values. Upsilon disk equals 0.81 plus or minus 0.05 m solar to L solar, and upsilon bulge equals 0.93 plus or minus 0.05 m solar to L solar, respectively, from Figure 1 of reference 20. For each plot of the galaxy rotation velocity, the Newtonian velocity curve is also displayed. Plots for the results of the spark galaxies can be found in Figures 2 and 3. Results for spark galaxy 6. Galaxy MB BTFR var MAE kg, M1010, M1010, KMS-1, KMS-1. NGC 2403 1.6121.6122.421.528.0.424 NGC 2841 37.277 37.3567.671.476 DDO 154 0.06474 0.021430.625.0.2250.578 NGC 2915 0.2810 0.27998.064 0.814 0.653. Table 1. Results of fits to spark galaxy data using the graviton model equation 82, with masses from equation 80 and equation 81. The VAR are the mean error of the reported stellar velocities. The MAE errors are the average absolute error for the fits. Using final velocity as flat velocity. Rotation curve does not flatten. Results for Spark Galaxy 7. Galaxy average dsk average Bullman dsk max dsk ngc 24030.5790.31.8 ngc 2841 1.0390.833 2.05.1 ddo 154 6.183 01.11.2 ngc 2915 1.8740 na. Table 2. Results of fits to Spark Galaxy data using the graviton model equation 82. The columns for dsk and Bull are the averages for the disk and bulge mass to light ratios determined by modeling the rotation velocity curve. 0 in the Bull column means the bulge velocity is 0 in the data. Min and max dsk values for high surface mass galaxies from reference 19. Na means the result is not available. NGC 2403. NGC 2841. Figure 2, NGC 2403 and NGC 2841. Fits with Spark data, the masses derived from equation 80 and equation 81, with velocity profiles for gas, disk and bulge. For mass to light curves, dsk is the solid line and filled circles, Bull is the solid line and open squares. For rotation velocity curves, the solid line is the minimized fit to the data with the graviton model equation 82, and the dashed line is the Newtonian velocity. Top half, upper, mass density. Middle, mass to light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Bottom half, upper, mass density. Middle, mass to light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Spark Galaxies DDO 154 and NGC 2915I. Two dwarf galaxies that have been difficult to understand in terms of missing mass are DDO 154 and NGC 2915. Figure 3 shows the results for the fits using the graviton model. The upper curve shows the mass density, the middle curve displays the m/l ratios, and the lower plot shows the observed and predicted rotation velocities. With the graviton model for DDO 154 we obtained a total baryonic mass of Bary is equal to 6.47 times 108 m, which is less than 2 times the detected luminous mass, reference, 21, of m** operator plus MHI plus he is equal to 3.65 times 108 m. Significantly, it is only 1/5 of the estimated dark plus luminous matter of dark plus lum is equal to 3.1 times 109 m. Our fitted disk mass to light ratios have an average of dsk equals 6.183 m/L, which is 3 times the published value of dsk is almost equal to 2 m/L. For NGC 2915 we obtained a total baryonic mass of Bary is equal to 2.81 times 109 m, where the stellar mass and luminous HI mass, reference, 22, reference, 23, MHI plus m** operator is equal to 1.06 times 109 m. Spark Galaxies DDO 154 and NGC 2915-2. This compares with the total dynamical mass MT is equal to 21 times 109 m, which is 7 times the total baryonic mass derived by the graviton model. DDO 154. NGC 2915. Figure 3, DDO 154 and NGC 2915. Fits with Spark data, the masses derived from equation 80 and equation 81, with velocity profiles for gas, disk and bulge. For mass to light curves, dsk is the solid line and filled circles. For rotation velocity curves, the solid line is the minimized fit to the data with the graviton model equation, 82, and the dashed line is the Newtonian velocity. Top half, upper, mass density. Middle, mass to light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Bottom half, upper, mass density. Middle, mass to light ratio. Lower, the model velocity versus radial distance from the galactic center and the Newtonian velocity. Discussion I. Regarding the baryon acoustic oscillations, BAO, in the primordial plasma and the resulting cosmic microwave background radiation, CMB, if the energy loss in the gravitational field due to the gravitational redshift of graviton energy is the cause of the apparent dark matter in the universe, implying that dark matter particles do not exist, then in density perturbations of the primordial plasma just before recombination, the baryons, photons, and gravitons are synchronized and there is not a central region of dark matter particles as theorized in the Standard Model, reference 24, so that when recombination begins the photons dissociate from the electrons and the resultant hydrogen atoms begin to attract and form dense regions in the perturbation. Just how the graviton redshift energy loss affects the density formations in the primordial plasma and how this affects the determination of the Hubble constant from the BAO and CMB modeling. Reference 25 is an area which needs to be studied. Discussion 2. Regarding galaxy dynamics, with the modified Newtonian dynamics, MOND, reference 26, 27, there may be a way to compare it with the graviton gravitational redshift theory. MOND takes effect in galaxies at a distance where the central acceleration is around 1.2 times 10⁻10 ms-2 by affecting a transition in the gravitational attractive force from AR-2 to AR-1 form. On the other hand, the graviton gravitational redshift theory augments the Newtonian rotational velocity beginning from the galactic center, which allows to distinguish it from MOND. Referring to Figure 2, at a radius of r equals 24.59 kpc, the spiral galaxy NGC 2841 has an observed velocity of v equals 298.0 km s-1, and we calculate the Newtonian velocity of Vn equals 191.5 km s-1 using the spark data. The radial acceleration at this distance is ACC equals v2/r equals 1.171 times 10⁻10 ms-2, which is at the beginning of the MOND regime and, assuming we have the correct baryon mass within that radius, MOND would predict an orbital velocity smoothly connected to the Newtonian value Vn, but we see that it would be smaller than v by 106.5 km s-1. Discussion 3. Another interesting alternative approach to modified Newtonian dynamics is given in reference 28, which, by way of an additive inverse Yukawa-like term to Newtonian gravitation, purports to account for gravitational dynamics from solar systems to galaxies and galaxy clusters and to the large-scale universe expansion. There is an analogy between reference 29 EQ 19 and our equation 54, which can be further explored. Conclusion I. The graviton self-interaction model describes the effect of gravitons in free fall in the gravitational field, losing energy by way of gravitational redshift and cosmological redshift without emitting any radiation. General relativity was applied for both the universe expansion and for spiral galaxy rotation curves. By assuming a coupling coefficient kdm for the graviton redshift in free fall, the graviton model can account for the apparent dark matter in the universe being related to the baryon density. Likewise, the dark energy depends on the coupling constant d and the baryon density. Thus, the apparent dark matter and dark energy are replaced by two constants and the hypothesized redshift of graviton energy. In the case of the rotational characteristics of spiral galaxies, the graviton theory well explains the greater than expected galaxy rotational velocities in the spark data with only the baryonic mass derived from the gas, disk, and bulge velocity data with fitted. Conclusion 2. Upsilon asterisk operator ratios, with a galaxy-dependent coupling coefficient Kg and with the total baryon mass conforming to the BTFR. It is apparent that the fundamental aspect of graviton redshift points to the need to include this in the general relativity field equations. Conflict of interest. The author declares no conflict of interest. References I. 1. Oliveira, F.J., 2022, The Theory of Gravitons in the Expansion of the Universe. JEPG, 8, 3. https://dx.doi.org/10.4236/jhepgc.2022.83041. 2. Oliveira, F.J., 2022, Theory of Gravitons in Spiral and Dwarf Galaxy Rotation Curves. JEPG, 8, 3. https://dx.doi.org/10.4236/jhepgc.2022.83055. 3. Doer, A. 2009, Implications of Graviton-Graviton Interaction to Dark Matter. https://arcs4.org/pdf/astro-ph/0901-4005. 4. Wikipedia, Lambda CDM Model. https://en.wikipedia.org/wiki/lambda-CDM Model. 5. Hubble, E. 1929, A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. Proceedings of the National Academy of Sciences, 15, 3, 168-173 https://dx.doi.org/10.73/PNAS.15.3.168. References to 6. Friedman, A. 1922, Über die Kehrung der Rams. Zeitschrift für Physik, 10, 377-386. https://doi.org/10.1007/bf0-133-2580. 7. Lemaitre, G. 1931, Expansion of the Universe. A homogeneous universe of constant mass and increasing radius accounting for the radial velocity of extragalactic nebulae. NRAS 91, 5, 483-490 https://doi.org/1093/mnrs/91.5.483. Translated from Lemaitre, Georges, 1927, Un univers homogène. Une de masse constante de rayon croissant rendant compte de la vitesse radiale de nébulieuses extragalactiques. Annales de la Société Scientifique de Bruxelles, A47, 49-56. 8. Robertson, H.P. 1935, Kinematics and World Structure. Astrophes. J. 82, 284-301. https://dx.doi.org/10.1086/1438681. References 3. 9. Walker, A.G. 1937, On Milne's Theory of World Structure. Proceedings of the London Mathematical Society, Series 2, 42, 190-127, https://dx.doi.org/10.112/poms/s2-42.190. 10. Einstein, A. 1918, Über Gravitationswellen. Sitzungsbericht der Königlich-Preußischen Akademie der Wissenschaften, Berlin, Seat 154-167. https://ui.adzabs.harvard.edu/abs/1918 11. Einstein, A. 1952, The Foundation of the General Theory of Relativity. Dover Publications Incorporated, New York. 12. Suzuki, N. Rubin, D. Lidman, C. Aldering, G. Amanullah, R. Barbary, K. et al., 2011, The Hubble Space Telescope Cluster Supernova Survey. D. Improving the dark energy constraints above Z greater than 1 and building an early type-hosted supernova sample. Astrophes. J. 746, 1, 220111768. https://dx.doi.org/1088/0004-63x/746/1/85. References 4. 13. The Cosmological Parameters, Chapter 21. Updated by O. Lahav and A. R. Little. https://pdg.lbl.gov/2011/rev-cosmological-parameters.pdf. 14. M. Tanabashi et al., 2018, Particle Data Group, Phys. Rev. D98, 030001. Field S, B.D., Molaro, P., and Sarkar, S23. Big Bang Nucleosynthesis, https://pdg.lbl.gov/2018/reviews/rpp2018-rev-bbang nucleosynthesis.pdf. 15. http://astroweb.cwru.edu/spark. 16. Lely, F., McGaugh, S.S., and Scombert, J.M., 2016, Spark, Mass Models for 175-disk galaxies with Spitzer photometry and accurate rotation curves. Astron J. 152, 6, 157-170. https://dx.doi.org/10.3847/00004-6-256/152/6/157. References V. 17. McGaugh, S.S., 2005, The Baryonic Tully-Fisher Relation of Galaxies with Extended Rotation Curves and the Stellar Mass of Rotating Galaxies. Astrophes. J. 632, 2, 859-871. https://dx.doi.org/10.1086/4329668. 18. Lely, F., McGaugh, S.S., and Scombert, J.M., 2016, The Small Scatter of the Baryonic Tully-Fisher Relation. Astrophes. J. Let. 816, 1, L14 L19. https://dx.doi.org/10.3847/2041-8205/816/1/L14. 19. De Block, W. J. G., and McGaw, S. S., 1997, The Dark Invisible Matter Content of Low Surface Brightness Disk Galaxies. NRAS, 290, 3, 533-552. https://dx.doi.org/10.93/mnrs/290.3.533. References 6. 20. Lee, P. Lely, F. McGaw, S. S., and Scombert, J. M., 2018, Fitting the Radial Acceleration Relation to Individual Spark Galaxies. Astron, and Astrophes. 615, A3. https://dx.doi.org/10.1051/0001732547. 21. Carrigan, C., and Putton, C., 1998, The Total Mass of DDO-154. Astrophes. J. 506, 1, 125-134. https://dx.doi.org/10.1086/306227. 22. Muir, G. R., Carrigan, C., Beaulieu, S. F., and Firmin, K. C. 1996, NGC 2915. 2. A dark spiral galaxy with a blue compact dwarf core. Astron J. 111, 1551-1575. https://dx.doi.org/10.1086/117895. References 7. 23. Muir, G. R., Blakesley, J. P., Sinani, M., Ford, H. C., Illingworth, G. D., Benitez, N., et al., 2003, The Discovery of Globular Clusters in the Protosporal Galaxy NGC 2915, Implications for Hierarchical Galaxy Evolution. Astrophes. J. Lett. 599, 2, L83, L86. https://dx.doi.org/10.1086/381317. 24. Beutler, F., Blake, C., Collis, M., Jones, D. H., Stavely Smith, L., Campbell, L., et al. The 6DF Galaxy Survey, Baryon Acoustic Oscillations, and the Local Hubble Constant. Mon. Not. Royal Astron SOC 416, 4, 3017-3032. https://doi.org/10.11/j.1365-2965-2011-19250. https://doi.org/10.111/j.1365-29662011.19250.x. 25. Planck collaboration, Aghanim, N, Akrami, Y, Ashdown, M, Amont, J, Baxigalupi, C, Ballardini, M, et al., 2020, Planck 2018 results. 6. Cosmological parameters. Asteron. Astrophes. 641a6, 67 to 139 https://dx.doi.org/10.1051/0041/2018333910. https://dx.doi.org/10.105/0004-6361/2018333910. References 8. 26. Milgram, M. 1983, A Modification of the Newtonian Dynamics as a Possible Alternative to the Hidden Mass Hypothesis. Astrophes. J. 270, 365-370. https dx.doi.org/10.1086/1611130. 27. Milgram, M. 1983, A Modification of the Newtonian Dynamics Implications for Galaxies. Astrophes. J. 270, 371-383. https dx.doi.org/10.1086/1611131. 28. Falcon, N. 2013, Modification of the Newtonian Dynamics in for Cosmology, an Alternative Approach to Dark Matter and Dark Energy. Journ. Mod. Phys. 4, 10-18. https://dx.doi.org/10.4236/jmp.2013.48a003. References 9. 29. Falcon, N. 2021, A Large-Scale Heuristic Modification of Newtonian Gravity as an Alternative Approach to Dark Energy and Dark Matter. J. Astrophes. Asteron, 42, 102. https://doi.org/10.1007/s12036-021-09752-0.